मोहित आवाज आ रहा है?
Yes sir, yes sir. Good morning.
गुड मॉर्निंग। सब ठीक?
अभी सर 7:30 तक people will join.
ओके, नो प्रॉब्लम।
Good morning sir.
गुड मॉर्निंग सर।
Good morning, sir. Good morning, Professor Mohit, Professor Gangwar.
Yes sir. Good morning sir.
Good morning.
Sir, thanks for coming online at such an early morning. So we still have, I think, 5 minutes. So let's wait for some time.
Good morning, sir.
Good evening, correct.
Hello,
Hey, how are you?
I'm doing great. How are you?
I'm good too.
Good. Can you hear me okay?
Yes, yes.
Good.
Palak,
Yes, sir.
please
Shall we
start.
start now?
Yes.
Good morning, everyone. I, Falak Khan, a student of MTech, Department of Applied Geophysics, IIT Dhanbad, welcomes you all to a 2-week course on global seismology under GIAN, Global Initiative of Academic Network. First off, we would love to have a moment to appreciate the interest and curiosity you all had put forward toward this course, and of course toward global seismology. Sometimes one encounters the belief that seismology corresponds only to the exact translation of the word the science of earthquake. However, this is far from the truth. Like most other sciences, seismology has also grown beyond its original boundaries. Now, to provide an insight to this, the course mentors have come up to unravel the secrets of seismology and earthquake. With this, I request our Honorable Director, Sir, Associate Dean, Head of Department Applied Geophysics, to inaugurate the course by pressing the green button.
So, Director, sir,
Sir,
is it there?
It is not working.
Yes, sir. I am going to press it on your behalf. Okay, so for everyone's behalf.
thank you so much, sir. Moving forward, I would like to request the Head of Department Applied Geophysics, Professor P.K. Khan, sir, to welcome the gathering.
A warm good morning to Indian expert and students, and good evening to US expert, Professor Derek Schutt. Professor Rajiv Shekhar, Director and Patron of the course. Professor Derek Schutt, foreign expert from Colorado School of Colorado University. Professor Mohit Agarwal, course coordinator. Professor Robi Gangwar, Associate Dean, Sponsored Research, and the brand ambassador of the course, the participants. I, on behalf of the Department of Applied Geophysics, welcome you all to this great course and its education values. The Department of Applied Geophysics was opened with the need of the exploration as well as solid earth geophysics research as for the country. In 1956, in the year of the International Geophysical Union, and over the last more than 6 decades, the Department of Applied Geophysics producing human resources and also in terms of R&D activity of India and abroad, and doing its excellence in the field of academics and research. Here, I have gone, after going through the course, I found the course is very much topical and need of the hours, because it is covering all the aspects, both in terms of exploration, seismic exploration, as well as solid earth geophysics, where you need to have the understanding of the seismology and its wave propagations. Here, you see, over the last 20 or 22 years odds, the globes, world faced number of great earthquakes, particularly the 2004 Sumatra earthquake and the Japan earthquake 9 magnitude. And there is a huge loss to the country. And subsequent, if you see, please stop the cross discussion. Please stop the cross discussion. And subsequently, you have experienced the 2015 Nepal earthquake, where there was a huge loss in adjacent countries as well as in India, and also equally the human life lost. So, to know better way with the modern technology like broadband seismograph as well as computer evolution, along with its data processing techniques, lot of new things are coming in the picture, like in terms of receiver function, waveform dispersion, then moment tensor inversion, as well as source dynamics characteristics understanding. So this course covering all the aspects, and its casualties happen to the society, like hazard, human hazard, earthquake hazard. So I hope this course have a great hope and for its success. And here I find few important aspects also, like attenuation, anisotropy, as well as its computer skills and its analysis. These are also very much important, because you see, when we go inside the earth, only the way to understand the earth, better way for seismic wave attenuation, because seismic wave attenuation now coming very fast with its new techniques to understand the anisotropy features inside the earth, which actually indirectly or alternatively to give a better understanding of the source dynamics, if somehow this anisotropy trigger the earthquakes. If you see in India and surrounding area, lot of areas are there, like Himalayas in the shield area, lot of anisotropic zones are there inside the earth, inside the below this Indian subcontinent. Also in the south of this area, Indian part, that is Indian Ocean, as well as Bay of Bengal, as well as Arabian Sea, where number of anisotropic zones are identified, and people globally trying to understand better way of this anisotropy, how these are responsible for Indian plate movements as well as generation of the earthquakes. So this course covering all the aspects, even reflection seismology also are involved here, which actually basically used for exploration purposes for oil and hydrocarbon, as well as other mineral deposits. So this is very important course, are very much topical for the students as well as young teachers. So I have a great hope of this course. Thank you, Professor Mahit.
Thank you so much, sir. Thank you very much.
Thank you so much, sir, for your words. Now I would like to invite local GIAN coordinator, Associate Dean, Sponsored Research, Professor Ravi Kumar Gangwar, sir, to tell us few words about GIAN.
Okay, thank you very much, Palak. So good morning to all of you. So first of all, we are really grateful to Professor Derek for accepting our invitation to deliver the series of special lectures and tutorials on the topic of global seismology under the MHRD scheme of the GIAN program. Basically, the GIAN is the global initiative for academic network. That is the program which is supported and approved by the government of India, with the aim that for tapping the talent pool of the specialized scientists and entrepreneurs, to encourage their engagement with the higher education institutes of the India, basically to enhance the country's existing academic resources, accelerate the pace of policy reforms, and elevate India's scientific and technological capabilities to the global excellence. So I can say that the participants which are basically going to be participants in this particular program, which is on the global seismology, they are going to be benefited all. So further, I can say that I am very sure that it would be a very grateful opportunity to all the participants to have the fundamental as well as the advanced lectures and tutorials onto the specific seismology topic, which is a very vibrant and the current need of the and of the any countries, that will not basically going to improve their knowledge, but also it is going to be how they choose their career into that particular academic or a specific research area. So with these words, I am really thankful to the Professor Mohit and the Professor Derek for taking this initiative and put a lot of effort to carry out this particular program. So thank you very much from my side.
Thank you, Professor Gangwar, for your wishes and the information on the GIAN scheme. Thank you very much.
Thank you, sir. Now moving forward, I request the course coordinator, Professor Mohit Agarwal, sir, to introduce foreign expert of the course.
Thank you, Falak. Honorable Director, sir, Professor Rajiv Shekhar, Associate Dean, Professor Ravi Gangwar, Foreign Expert, Professor Derek Schutt, Colorado State University, Head of the Department, Applied Geophysics, Professor P.K. Khan, all the participants, friends in the audience. I would like to welcome you all to the inauguration ceremony of GIAN course on global seismology, which will run for 10 days until May 18, starting from today. A total of 18 lectures and 9 tutorials will be conducted under this course. We are having 2 sessions for this course on each day. Morning session is for lectures between 7:30 a.m. to 9:30 a.m., while evening session is for tutorials between 7:30 p.m. to 9:30 p.m. We received an overwhelming response for the course registration from all across the country, and a total of 40 students registered for the course. I am immensely thankful to Derek that he kindly accepted my invitation to deliver all lectures early morning and late evening. We have a 13-year-long relationship since summer 2008 when I did summer internship under him. To introduce audience with the foreign expert, I would like to read out his brief CV. Dr. Derek is a professor of geosciences at Colorado State University. His research interests involve using seismology and geophysics to infer lithospheric and asthenospheric temperatures, compositions, fabrics, and velocity structures. Currently, he is a part of 2 $1 million plus funded multi-institution collaborations. The first is an international field project to understand the causes of orogenesis in the sparsely sampled Mackenzie Mountains in northwestern Canada. The second is to create detailed maps of temperatures, densities, and other physical state observables as part of a project to build a global geodynamical reference model. At Colorado State University, Dr. Derek Schutt teaches seismology, geodynamics, and an introduction to geophysics class, along with running a topical seminar every other semester. He is also the Master Teacher Initiative Coordinator for the College of Natural Sciences, which involves a weekly teaching tip to help instructors bring the latest in education research into their classes. The GIAN course is a concise version of 15-week-long seismology class taught every fall at Colorado State University. Dr. Schutt received his PhD in 2000 at University of Oregon, working with Eugene Humphreys. He was a Harry Wood postdoctoral fellow at the Carnegie Institution of Washington, working with Drs. David James and Paul Silver, then moved to a postdoctoral fellowship and research scientist position at the University of Wyoming, where he worked with Dr. Ken Duker. Next, he took a position as a geophysics program director at the US National Science Foundation. Dr. Schutt became an assistant professor at Colorado State University in 2008. Dr. Schutt also received his BS in mathematics and a BA in physics. Thank you so much, and let's move forward. Now to Falak Khan.
Thank you so much, sir. Moving ahead, I would love to invite Professor Derek Schutt, our foreign expert for the course, to give us more insight into the course.
All right. So this course is a synthesis of a course I teach every semester that is 3 lectures a week and 2 hours of computer work a week. We won't be able to expend that much time, but I think I've managed to narrow down the lectures and the computer work to the essentials. The course focuses on global seismology and developing the theories behind seismic wave propagation that I hope you can use for whatever desires that you have in seismology. We will also learn some basics of Unix and Linux, some details how to get seismic data. One of the things in the United States, all seismic data collected by experiments is publicly available, and that would include to all of you. So we will practice getting data and doing some processing on it as well. Yeah, I think that's all I have to say right now.
Okay, thank you so much, Derek. Now over to Falak.
Thank you so much, sir. With this, I request our Honorable Director, Professor Rajiv Shekhar, sir, to address the gathering.
Thank you very much, Falak. Professor Derek Schutt from the Colorado State University, Dr. Mohit Agarwal, who is offering the course along with Professor Schutt, Professor P.K. Khan, head of the Department of Applied Geophysics, Professor Ravi Gangwar, and all the other participants. I mean, I was very happy to hear from Derek that he's going to have tutorials where they're going to use the computer to process seismological data. In IIT ISM, one of the things we are stressing on is the use of computers for modeling a process, for better understanding the dynamics of a system, and in engineering for scaling up for commercialization. So I was extremely happy to see that along with the lectures, there are 9 hours of tutorials using computer work. And I hope this course will help our students get a better understanding of how to predict earthquakes, and then in a way, then later on develop systems that will help save lives. So again, I would like to congratulate the course coordinator, Dr. Mohit Agarwal, and Professor Derek Schutt. And Derek, a warm online welcome to IIT ISM Dhanbad. Thank you very much.
Okay, thank you, Director sir. Now I am, please over to Falak.
Thank you so much, sir. We are delighted with your words. So now I hope we all are excited about the course and are ready to explore and learn the interesting concept of seismology. So without further ado, let's dive deep into this course, and thank you everyone. Now hand it over to Professor Mohit Agarwal, sir, for vote of thanks.
Yeah. Thank you so much. I would like to first thank to the GIAN committee for providing funding to organize this course. Also, my sincere thanks goes to the director, sir, Dean R&D, Associate Dean Professor Ravi Gangwar, and Associate Dean Sponsored Research and Research Infrastructure, Professor Sagarpal, to provide necessary support and infrastructure to start this course successfully. I also can't thank enough to Professor P.K. Khan, our HOD, Applied Geophysics, who has always supported this course and also provided several important suggestions to successfully conduct this course. And not only that, I would like to thank the students, especially Ravindra Gupta, Rajnish Mole, Hariom, Aman Khan, Rashish Shams, Falak Khan, and Iya Rasool, who were always there from the very beginning to help me successfully accomplish several activities related to this course. Thank you all. With this, we are going to culminate this inaugural session, and we'll go into the lecture. Thank you so much, everyone, for coming to join us at such an early morning. Thank you so much.
All right, should I start?
Yes.
Okay.
Now you can share your screen for the presentation.
All right, I will do that. Oh, excuse me, I need to give my computer permission to share the screen. I have to leave the meeting and come right back.
Okay, no problem. So we'll have to wait for some time to start the lecture 1. I think there is some permission issue with this computer, so he will be just right back. Thank you.
All right. Can you see a slide?
Yes.
All right, great. So today I will present the development of seismic wave theory. And this lecture and the next hour's lecture will probably be the most complicated lectures that I will give in this class. And I would ask that you be patient with yourselves and realize that you may or may not understand it all, and that's fine. And I would encourage you to go through the PDFs in the shared OneDrive. And then once you've done that, if you have any questions, feel free to email me and also just ask me during the lecture or after the lectures. All right, so we're going to start with the elastodynamic equation and propagating waves in an elastic medium. And to do that, we need to develop the concept of stress and strain. So stress is a 3x3 tensor that describes the force per unit area on a material. The traction vector is the surface force per unit area on a plane with a given normal. So a normal vector to that plane. The traction can be calculated using Cauchy's stress theorem. So the traction equals the stress tensor times the normal vector. And then we will use the engineering convention that tensional stress is positive. So stress in the earth is going to have negative components using our convention. Other books and other lessons may use compression being positive, but in this case, we will use compression negative. So these are all topics that I will cover shortly, but I wanted to give you an overview of what I will cover. So properties of the stress tensor, it is symmetric. We can rotate it into another coordinate system. And in particular, there's a coordinate system that has no shear stress. And this gives the principal stresses, which are the eigenvalues of the stress tensor.
Derek, actually, your slides are not changing. You are still at the first slide for us.
Oh, really?
Yes.
Okay. Let me see here. Sorry about that. I have a laptop connected to a monitor, and I think I just need to use the laptop. So I will disconnect the monitor and go from there. All right, can you see a slide now?
Not yet.
No, okay. Can you see a slide now?
No.
All right, let me try sharing the screen again.
Yeah, now it's coming.
Okay.
Is it
All right,
possible
sorry about that.
Yeah, now it's fine.
Okay.
Yeah, now it's changing. Thank you.
All right, great. So properties of the stress tensor, it's symmetric. We can rotate it into another coordinate system. And in particular, there's a coordinate system that has no shear stress on it. This gives the principal stresses, which are the eigenvalues of the stress tensor. The trace of the stress tensor is independent of the coordinate system used. The pressure is the mean of the trace of the stress tensor, and the deviatoric stress tensor is the stress tensor minus the pressure. Units of stress are newtons per square meter or pascals, and roughly a 33 kilometer increase in depth increases pressure by about 1 gigapascal. All right, so that was a quick overview of what we're going to cover with stress. So consider a body of material, and here I'm showing this sort of blob of material. There are two types of forces that can act on the body. There are body forces, which act on every part of the body. So gravity is a good example of this. And a body force does not require contact for its transmission. And there's also surface forces, which are transmitted on the body of this body, the boundary of this body. So F1, F2, and F3 are good examples of the surface forces. Now, if we chop off the right side of the body, we can represent the effects of the missing right side by an equivalent set of surface forces. So we will look at this red circle here, and we will expand it, and we will consider an infinitesimal element in our plane. And this element has an area delta A and a normal to it given by the normal vector in with a hat or tilde over, or not a tilde, I forget what the mark is called. And we can define the traction vector on any area element as the force on the element divided by the area in the limit as the area goes to 0. So down here at the bottom, I have a formula for the traction vector. It's going to be a function of the normal or the direction that our plane is oriented. And it's just the limit of the force as the area goes to 0. And it has 3 components: an X component, a Y component, and a Z component. Now, the traction vector can be decomposed into components parallel to the surface, which gives you the shear stress, and that's shown by the red arrow, and normal to the surface, which gives the normal stress, and that's shown by the blue arrow. And the traction vector is a combination of the normal stress and the shear stresses. Now, the traction vector is going to depend on the orientation of the plane used. So, for example, here is an example of a plane with a normal in the X direction. So the normal vector is pointing in the X direction, and we would have the traction vector based on that plane. And we can define the stress components on this X plane. So the normal stress is basically the normal traction vector on this X plane. And then the shear stress is the component in the Y direction of the stress or traction vector, and a component in the Z direction of the traction vector. So thus we have a component of our shear tensor or a stress tensor. The first letter gives the direction of the normal to the plane that we're using. And then the second letter gives the direction of the force. So we can do this for the y plane and the z plane as well as the x plane. With 3 possible planes to consider and 3 possible directions for the traction vector to be resolved in each plane, this gives us 9 stress components to define the state of stress at any given point. So sigma xx, sigma xy, and sigma xz give the component of stress in the x, y, and z direction on plane x. Sigma yz, sigma yy, and sigma yx, sigma yy, and sigma yz give the x, y, and z stresses on plane y, and so on for plane z. We can also write, rather than use x, y, z, to use 1, 2, 3 to denote the coordinate axes. This is a mathematical convenience that we will come back to. But basically 1 means x, 2 means y, 3 means z. All right. So here I'm going to use tau instead of sigma. So I'm going to use this sort of, this T-shaped letter instead of sigma, just because both letters are used to denote stress in different publications. And I will use them interchangeably. In this case, I will use tau because that is what's in this figure that I'm using. Now, if there's no rotation, tau of 3, 2, so tau on the face with a 3 normal or the z normal in the 2 direction or the y direction is going to equal tau on the 2 face in the 3 direction. And that will keep the block, the element, from rotating. Otherwise, if this was unbalanced, we would have a rotational acceleration. And we are going to assume that we have no rotational acceleration. So that means that several terms in the stress tensor must be equal. So tau sub 2, 1 or sigma sub 2, 1 has to equal tau sub 1, 2. Tau sub 1, 3 has to equal tau sub 3, 1. And tau sub 3, 2 has to equal tau sub 2, 3. So this makes the stress tensor symmetric. What this means is we are left with 6 independent parameters. The ones on the trace here give the normal stresses, and the ones in the green triangle here give the shear stresses. All right, so that is a quick overview of the stress tensor. Now, strain defines the deformation of a material in response to stress. So we will look at how strain can be defined in terms of a displacement U, and how U varies with location defines the type of strain or the shape of the deformation. And elasticity, which is a third tensor, will determine the amount of strain a given stress will cause. So once we understand strain and we understand elasticity, we can think about wave propagation. So we will talk about deformation, U, which is a vector, and X, which X actually defines X1, X2, X3, so X is a vector as well. And we will assume that deformation varies smoothly from point to point. And so if U of X is a deformation at location X, so for instance, if I have a location X and then I deform it, so the point at position X is going to be now at X plus U of X, then at U of X plus du of X, we'll give the deformation at location X plus dx. So if I move a small amount away from point X by dx, I'm now at X plus dx, and the deformation will be of U of X plus dx. And here I'm just giving a bunch of definitions. And now with that in mind, we can define the strain tensor. The strain tensor in 1, 2, 3 notation or an XYZ notation, each one is interchangeable, gives the deformation as I move in the X1 direction. So du1, dx1 gives deformation in the one direction as I move in the X1 direction. This next term here, 1/2 du1 dx2 plus du2 dx1 is 1/2 the deformation in the one direction as I move in the X2 direction, plus the deformation in the two direction as I move in the X1 direction. And you'll note that this upper term here looks a lot like this term here. So the strain tensor is symmetrical just like the stress tensor. Basically, there are 6 free components. All right, I want to briefly introduce you to Einstein summation notation, or also it's called implied summation notation. And we will use this in a lecture or two. So its utility in terms of vector calculus is actually quite high. So we're going to introduce it. So basically, if I have a term a sub ij, b sub j, if I repeat a letter or an index twice in a term, so in this case, the j is repeated, that means sum over this term where j varies from 1 to 3. So a sub ij, b sub j in summation notation equals a sum of j equals 1 to 3, a sub ij, b sub j, which just equals a sub i1, b sub 1, plus a sub i2, b sub 2, plus a sub i3, b sub 3. So this twice repeated index is called a dummy or implied summation index. And it's always repeated twice in a term. A free index is used only once. So in this case, I is a free index. I can vary from 1 to 3 as well. But in this case, we would have a different equation for I equals 1, I equals 2, and I equals 3. And I note that a term or component of a mathematical equation that is multiplied or divided is a term, but not something that is added or subtracted. So xy squared is one term, but x plus y squared is 2 terms. Rule 3, no index may occur more than 3 or more times in a given term. And rule 4, the free indices on both sides of an equation must match. Okay, so we've quickly looked at stress, we've looked at strain. So stress is the force per unit area, and strain is the response of our elastic medium to this force per unit area. And the relationship between stress and strain is defined by the elasticity. So we can think of it in terms of Hooke's law. So F equals kx for a spring. You might have seen that in physics class. So in this case, we are going from a one-dimensional spring equation to a three-dimensional earth. So F, or force, is analogous to stress. K, which is your spring constant, is analogous to C sub ijkl, which is a fourth order elastic tensor. This describes the elasticity of the medium. And then X is analogous to strain. So this is the deformation due to an applied stress. Thus, the relationship of stress to strain is equivalent to F equals KX, or in this case, sigma sub ij equals C sub ij KL times E sub KL. So sigma is the stress, C is the elasticity tensor, E is the strain tensor. And you'll note here, and C times E, there are two terms, two indices repeated, K and L. So this means that we will have to do an implied summation over K and L, and that's what's given by the non-Einstein summation notation formula below this. All right, so we've mentioned that stress has 6 independent terms because sigma sub ij equals sigma sub ji. Strain also has 6 independent terms because E sub KL equals E sub LK. And this implies that C sub ijkl equals C sub jikl, and C sub ijkl equals C sub ijlk. There's another symmetry that comes from thermodynamics. C sub ijkl equals C sub klij. So C is a 4th order tensor, and a tensor has 3 to the order of components. So a 2nd order tensor is 3 to the 2nd, or 9 components, and a 4th order tensor has 3 to the 4th power terms, or 81 terms. But these symmetries mean that the elasticity tensor only has 21 independent terms. So we've simplified things from 81 terms down to 21 terms. Now, if our medium is isotropic, that is, the properties don't vary with direction, there are only 2 independent parameters. And one way we can define the 2 free parameters is via the Lemay constants, and that is given by lambda and mu. Lambda is just called a Lemay constant or Lemay parameter, and mu is the shear modulus. And we can relate the components of the elasticity tensor to lambda and mu using this equation here, where we use delta sub ij as a Kronecker delta. So delta sub ij equals 0 if I doesn't equal j, and equals 1 if I equals j. So we can rewrite Hooke's law for an isotropic elastic solid, sigma sub ij equals C sub ijkl times E sub kl, as sigma sub ij equals lambda E sub kk delta sub ij plus 2 sub mu E sub ij. And here we've just taken that first equation that I gave you here and just plug that in for C. Now E sub kk has a repeated index, so it's an implied summation for k equals 1 to 3. And we can also, this is basically the trace of the strain tensor. So it's E sub 1, 1 plus E sub 2, 2 plus E sub 3, 3. And we sometimes call that theta, where theta is the dilatation. So theta equals E sub 1, 1 plus E sub 2, 2 plus E sub 3, 3, which is the trace of the strain tensor. And if I go back to the strain tensor defined in terms of U and X, this is just du1 dx1 plus du2 dx2 plus du3 dx3, which is just the divergence of U, or your deformation function. All right, so we've really quickly defined stress, we've defined strain, and we've related stress to strain through elasticity. Now, the next thing we need to do is derive an equation for elastic waves. So we will start with the homogeneous equation of motion. And the way we would do that is we would relate ground motion U to stress sigma. We will do this by relating force to stress. Then we will relate force to acceleration via force equals mass times acceleration. And that would give us the homogeneous equation of motion. So here's how we would relate force to stress, right? So if stress per unit area, if stress is force per unit area, then stress times a unit area is going to give us a force. And then we can calculate mass times acceleration. And in this case, since we're talking about an infinitesimal element, we will talk about the acceleration of a given component times its density. And that is going to be equal to the derivative of the stress tensor. Next, to calculate the elastodynamic equation from the homogeneous equation of motion, we will take the stress side of the equation and relate it to strain. And then we will relate the strain side to U. And since the strain tensor consists of the spatial derivatives of U, then we have both sides of the equation with U on it. And that leaves us with the simplified elastodynamic equation, which is this here. So it looks kind of complicated, but this is solvable. So the two Lemay parameters, so this is for an isotropic substance, lambda plus mu times the gradient of the divergence of U equals the shear modulus times the Laplacian of U, and that equals the density times the acceleration of U. Now, I've given you in 3 slides what I would take normally 2 lectures to do. So what we've just done is a quick overview of how we would get to this equation. And now we will solve the equation. We will do a Helmholtz decomposition. And we will divide U into a vector potential and a scalar potential. So we will assume that U, which is our deformation function, can be divided into a scalar potential, which is phi, and a vector potential with this, which is psi. And U equals the gradient of phi plus the curl of psi. And this actually lets us break the elastodynamic equation into 2 separate and simpler forms. The one for scalar potential, which gives us p waves, is the Laplacian of phi minus 1 over alpha squared, where alpha is the p wave velocity, times d squared phi dt squared, and that equals 0. So this gives us a simpler formula of the initial equation that we derived. And now we can try and solve this. One solution is a monochromatic wave in potential. So phi sub x in t equals a times e to the I times omega t plus or minus k dot x. Here omega is angular frequency. So it's equal to 2 times pi times f, which f is the frequency. K is the wave number vector. So it's got 3 components, and we'll talk about this shortly. And x is a vector that indicates position, and then t indicates time. The velocity alpha is the square root of lambda plus 2 mu over density, or in terms of something a little more useful to you guys later, it's the square root of the bulk modulus plus 4/3 times the shear modulus over the density. Now the equation for vector potential, or S waves, is going to look a little similar, except here we have a vector field. And beta is now the S wave velocity. So the P wave velocity is alpha, the S wave velocity is beta. This has solution psi sub as a function of x and t equals b, which is a polarization vector, and it can vary with frequency, times our harmonic wave, which is E times I times omega t plus or minus k dot x. So this E term is similar to what we had with the P wave equation. Now the S wave equation has a wave propagating at this velocity, beta equals the square root of mu over density. So alpha, the P wave velocity, equals k plus 4/3 mu over rho. And then beta, the shear wave velocity, equals square root of mu over rho. And mu is the shear modulus. All right, let's talk about what the wave number vector means. So it's a vector, so it has 3 components. And here I'm just doing it in 2 dimensions. So it has magnitude square root of k1 squared plus k2 squared. In 3 dimensions, this would also be plus k3 squared. And it gives us a vector that gives the propagation of the direction of propagation of the wave normalized by omega divided by alpha in the case of a P wave, or omega divided by beta in the case of an S wave. So K vector equals omega over alpha times the unit vector, which gives the direction of propagation of the wave. It's also useful to define the slowness, which is the reciprocal of velocity. So the slowness vector equals S, which is the direction of propagation, divided by the velocity. Here I'm using C as an arbitrary velocity, where we would use alpha for P waves and beta for S waves. With that in mind, I can rewrite the S wave potential, which is B of omega E times minus I omega t minus omega S dot x, which is the slowness vector times the position vector. I can also rewrite that as, sorry, this should not have an equal sign in it. It should just be B sub omega E to the minus I omega t minus k dot x, where we use the wave vector instead of the slowness vector. So this one has omega multiplied by both terms, and this one has omega only multiplying the t term because k has omega in it. All right. So we've defined equations that solve the elastodynamic equation, but these equations are for potentials. So we have phi and psi as potentials. And that doesn't actually tell us how a bit of the earth moves. So what we want to know is what the displacement function u is. So to get at particle motions, if we have the functions defining the potential, then what we do to get the particle motions is to reverse the Helmholtz decomposition. So for P waves, the particle motion due to a P wave is the gradient of the scalar potential. And for S waves, the particle motion is the curl of the vector potential. Now, if I consider a P wave traveling in the x direction, it satisfies the P wave potential equation, del squared phi minus 1 over alpha squared equals d squared phi dt squared equals 0. And if it's traveling only in the x direction and not the y and z directions, we can get a general solution that looks like phi equals 5t plus or minus x over, this should be alpha. So sorry, that says a, but it should say alpha. We can rewrite that as a wave moving in the plus x direction and a wave moving in the minus x direction. And then we can take the gradient of this phi. And here I've taken the gradient. So the gradient is d phi dx, comma d phi dy, comma d phi dz. So the gradient is the direction of steepest descent. And because phi up here is only a function of x, not a function of y and z, then d phi dy and d phi dz are both going to equal 0. So u, our displacement, is only going to have an x component, not a y or z component, and that will be equal to d phi dx. So for instance, if phi is given by this harmonic term, so e to the I minus omega, e to the I omega t minus k sub x times x. So the wave is only propagating in the x direction. So we only need the x component of the wave number vector. Then d phi dx, which gives us the displacement, is just going to be minus I k sub x e times I times omega t minus k sub xx, which means u equals minus I k sub x times phi. So what this means is that if I have a wave propagating in the x direction, which is given by k sub x, that particle motion, so the direction at which the Earth vibrates in response to this propagating wave, is also in the wave propagation direction. And that is given by the fact that u only has an x term here. So this means that for a P wave, particle motion is in the wave propagation direction. We can do the same thing for S waves. So here's the S wave equation. And let's say the S wave has an arbitrary vector potential, psi sub x, psi sub y, psi sub z. And we will assume an S wave propagating along the x direction. So k, our wave number vector, just equals k in the x direction, 0 in the y, and 0 in the z direction. So that means psi equals b sub b as a function of omega times e to the minus I omega t minus k sub x times x. So if we had a k sub y and a k sub z, then this would also be minus k sub y times y minus k sub z times z. But since this wave is only propagating in the x direction, we just have to take into account k sub x. So if the potential is only a function of x, then sigma x, psi sub x, psi sub y, and psi sub z are all just going to be functions of x. And displacement is going to be the curl of psi. That's just reversing the Helmholtz decomposition. And that will give me a displacement in terms of u sub x, u sub y, and u sub z. But u sub y and u sub z are just functions of x. So all the derivatives with respect to y and z will vanish. And if you do the math, you will find out that the displacement is 0 in the x direction, d psi sub z dx, and d psi sub y d in the y direction, and d psi sub y dx in the z direction. So what this means is particle motion for S waves is perpendicular to the wave propagation direction. So to summarize, P waves cause deformation in the direction that the waves are moving. So in this case, the wave is moving in the x direction. S waves cause motion perpendicular to the direction that the wave is propagating. The S wave field can be decomposed into SH and SV waves. So the SH wave is a horizontally polarized shear wave, and SV is polarized in the station to receiver plane. So I'll show you what that is in a second. So SV is always perpendicular to the propagation direction and in the vertical plane containing the ray path. So if I have an earthquake given by this star here and a seismometer given by this cone, the SV direction is going to be perpendicular to the ray path, and the SH direction is going to be perpendicular to the SV direction and along the direction of the surface of the earth. Now for a vertically propagating wave, SV then becomes horizontal because the wave is propagating perfectly vertical, and so the perpendicular to that is going to be horizontal. All right, so what we've learned very quickly is we've defined stress and strain tensors, and we related them through the elasticity tensor. We wrote down the elastodynamic equation, which was this. This is sort of complicated. To solve it, we did a Helmholtz decomposition on U, which solved the equation with two separate terms. So the vector potential term and the scalar potential term. We noted the solution for P waves and S waves. So this is the scalar potential term solution, which gives you P waves, the vector potential term, which gives you S waves. And then to get the actual P and S wave displacement, we calculated the gradient of the scalar potential and the curl of the vector potential. Using these two equations, we then noted that P and S wave particle motion would be along the direction of propagation in the P wave case and perpendicular to the direction of propagation in the S wave case. All right, I'm going to take a 5-minute break and start my second. I'm going to take a 5-minute break and start my second lecture in 5 minutes. That was probably the most complicated lecture we will get to. So I don't, unless you've seen it all before, I don't expect you to fully understand it, but see if you can go through the main points as I outlined at the end of the talk and try and understand some of the basis for me coming to those main points. All right.
Okay, thanks, Derek. So we are going to meet after 5 minutes.
Yep.
Okay, thanks.
Excuse me, sir.
Yeah.
Sir, we have an elastodynamic equation and it looks very similar to the normal wave equation. So there are some extra terms in the elastodynamic equation. So what does those extra term means?
Well, in the isotropic elastodynamic equation, the lambda and mu terms end up becoming in the alpha and beta terms in the seismic velocities. So those terms are still in the solutions given by the wave potentials. Does that make any sense?
Actually, I'm not getting, sir. Okay, so there was an extra term, I think, lambda plus mu into delta and divergence of u, that is displacement.
Yeah, so one I should say, I skipped the solution. So
Okay.
I basically gave you guys the elastodynamic equation, and then I gave the solution to the elastodynamic equation from the Helmholtz decomposition. So I have notes that I could post on the OneDrive link where I actually go through and solve the elastodynamic equation. But the lambda plus mu ends up in the beta and alpha terms of the potential equations, which then ends up in the beta and alpha terms of the P wave and S wave displacement equations.
Yes, I got it. Thank you, sir.
Yep.
So could you please post that solution that you just cited?
Yeah, I will. I'll do it after class.
Yes, sure. Thank you. Also, so there's a small question I had. Would you like to take it now?
Sure.
Okay. So when you spoke about the stress and strain tensors, there were 3x3 each, right?
Yes.
So why can't we just have a 3x3? I mean, the constant tensor that would relate, the stress to strain, like the Hooke's law part of it.
So it turns out that we need a 3x3 tensor to relate every component of the stress tensor to the strain tensor. So we need 9 components to relate each component of the stress tensor to each component of the strain tensor. So then we have 9 components times 9 components equals 81.
I'm not really able to get a clear insight on why that's happening. So could you like recommend some sources which could, take me to the basics of this?
Mm-hmm. Yeah, I'll think of something, and I'll post my lecture on elasticity as well, where I go through things in a little more detail.
Yes, sure. Thank you so much.
Yep.
Okay, guys, we are going to meet after 5 minutes.
Yeah, so we have another, what, 2 minutes?
Yeah, maybe. Yes. Would you like to have a 5 minutes break?
Yeah, actually, I'll take a 2-minute break or 3-minute break, and I'll be right back.
Okay, sure. Thank you.
All right, shall I start again? I'll wait another minute. All right, everyone. I think I will start again. So this lecture will cover some of the basics of seismic wave propagation. And this is actually going to be a fairly long lecture, so we may not finish it tonight, or well, sorry, this morning for you guys. And that's perfectly fine because my subsequent lectures will be a lot shorter than this one. So I guess with that in mind, I will go ahead and start this lecture. Oops. Can you all see a slide that says basic ray theory, reflection, and transmission?
Yeah.
Yeah, okay. All right. So this sort of longish lecture, I want to go over just basics of ray theory, reflection and transmission. So how much energy is reflected or transmitted at an interface. And I also want to talk about evanescent waves. And evanescent waves will lead us to surface waves. So the goals of this lecture are to talk about wave propagation directions in a medium, what happens at an interface, and then evanescent waves, which are waves that travel along an interface. To use this, we will use ray theory. It's an approximation to actual wave propagation, and it allows us to consider the path energy travels through the Earth. It works at a variety of scales, from industry seismics in a sedimentary basin to the path of P waves through the outer core. In theory, it's only applicable to infinite frequency waves, but in reality, it's applicable to most waves. So it's simple. It's useful for many problems, such as determination of Earth structure, locating earthquakes, tomographic inversions, where you actually take the earthquake arrival times and infer the velocity of the Earth that the energy traveled through. It is an approximation, however, and it does not do well when heterogeneity on the order of a wavelength or less exists. It doesn't explain wavefront healing, diffraction, or do well in the presence of steep velocity gradients. With that in mind, we will introduce Snell's law. So if an SH wave is vibrating parallel to an interface, then any reflected or transmitted wave produced by the incident SH will also be an SH wave. However, SV and P waves are coupled to each other. So a P wave can create an SV wave and vice versa. So in many cases, we'll talk about PSV waves as a common system and SH waves as an independent system. So consider a wavefront at times T0 or T naught and T sub 1. So here it is at T naught, here it is at T sub 1. It travels a distance delta S, and the surface distance that it propagates is delta X. And the angle with respect to the surface is theta. By trigonometry, delta S over delta X is going to be the sine of theta. And so delta X sine theta equals delta X, delta S, which equals the velocity times the travel time, just because rate times times equals distance. And delta T over delta X, which is the sine of theta over V. So if I just solve this equation and I divide by V, I get sine of theta over V, which we call P. And P is the ray parameter. 1 over P equals the velocity that the wave travels along the surface of the Earth. If we define the slowness as U equals 1 over V, and then sine theta over V equals U sine theta. So that's just because I translated 1 over V into U. This is different from displacement. This is a different U. This is also in the textbook I use, Stein and Weiss session. This is given as S, but other books will use U for slowness. So imagine I have a wave following this wave path. So the ray path is perpendicular to the wavefronts, and it travels through an interface. So the top layer has velocity V1, the bottom layer has velocity V2, which is greater than V1, and the wavefronts that are assumed to be continuous. So if that's the case, sine theta 1 over V1 is going to equal sine theta 2 over V2. Or P1, the ray parameter of the ray in the top layer, is going to equal the ray parameter of the ray in the bottom layer. So what we've shown is the ray parameter for a given ray remains constant along its path. And we can calculate the angle that the ray travels from Snell's law, which is sine theta 1 over V1 equals sine theta 2 over V2, where theta 1 and theta 2 are the angles of incidence with respect to a vertical that is, it's vertical to the interface. Now, we will recall that the wave number K equals omega over V. We can decompose this into the horizontal and vertical components of K. So K sub Z equals K cosine of I, Kx equals K sine of I, where I here is the angle between the surface and the wavefront. Oops. And then C sub X and C sub Z represent the horizontal and vertical apparent velocities of the wavefront. So as this wave here propagates forward, it's going to, the intersection with the surface is going to move at velocity c sub x. And the interface direction with respect to the vertical is going to move at velocity c sub z. If I have a perfectly vertically propagating ray, then c sub x will be infinity because the wavefront will be observed at all points at the same time. If I have a horizontally propagating wave, the velocity of the wave that is actually traveling will be equivalent to the velocity it propagates at the surface. So c sub x is going to equal v. So we can redefine the slowness vector as the vertical and horizontal components. So the slowness vector, u, again, this is not the displacement vector. This is a separate vector, but it also indicated by u. And that equals, in 2 dimensions, the ray parameter and then eta. And the ray parameter is sine theta over v. And this is going to be constant for the ray. And then eta is cosine theta over v, and this will vary in each layer. So this is 1 over the horizontal wave propagation velocity and 1 over the vertical wave propagation velocity. And u can also be converted into the wave vector using this formula. So u sub x equals k sub x over omega, u sub y u sub z equals k sub z over omega. And here we're just doing it in 2 dimensions. So horizontal slowness is 1 over the horizontal apparent velocity, which is the ray parameter, which is constant for a ray. Vertical slowness is the velocity, is going to vary with the velocity of the layer, and that's 1 over the vertical apparent velocity. But note that slowness is not 1 over the vector component of velocity. So you have to decompose your slowness vector in terms of the ray parameter and eta, or these terms next to ray parameter and eta. We can define some useful relationships between eta and p, starting with the equality 1 over velocity squared equals cosine squared velocity plus sine squared velocity. Here I'm just using the trig identity that cosine squared plus sine squared equals 1. And that equals cosine squared theta over v squared plus sine squared theta over v squared. And cosine squared or cosine theta over v is eta, sine theta over v is ray parameter. So 1 over the velocity squared equals eta squared plus p squared. So the magnitude of the slowness, u sub squared, equals 1 over the velocity squared. That means the magnitude of the slowness equals the absolute value of the square root of p squared plus eta squared. And since 1 over v squared equals eta squared plus p squared, as we showed in the last slide, then eta, which equals cosine theta over v, can also be written in terms of the square root of 1 over v squared minus p squared. So the intuitive meaning of ray parameter, p is 1 over the horizontal apparent velocity. In this case, if our ray is propagating horizontally, it's just 1 over the true velocity. Here, if ray parameter, if we have a vertically propagating wave, so it's moving upwards, then the ray parameter is sine theta over v, but v sub x, sine of theta equals 0, so the ray parameter equals 0. And v sub x, which is the horizontally propagating velocity, is going to be effectively infinity. So ray parameter can be thought of as 1 over v sub x, which is 1 over infinity, which is going to be equal to 0. Now, for a more complicated Earth, we can often model it in terms of a series of layers. So imagine we have a velocity gradient. We can model it in terms of a bunch of little steps. And because the ray parameter is constant, then we can note sine sub theta 1 over v1 equals sine sub theta, or sine of theta 2 over v2 equals sine of theta 3 over v3, and so on, up to layer I. If velocity keeps increasing with depth, then we can calculate theta sub I plus 1 equals the arc sine of v sub I plus 1 over v sub I times sine of theta sub I. And that's just solving the Snell's law for layer I plus 1. Now, at some point, sine of theta is going to approach 1. If as it approaches 1, that means theta sub I plus 1 is going to be 90 degrees, and the ray will travel horizontally along the interface. If sine of theta sub I times v sub I plus 1 over v sub I is greater than 1, that means that theta I plus 1 is not defined, because the arc sine of this, of something greater than 1, is not defined. And that means all the energy reflects rather than is transmitted. So we've discussed how a ray propagates in the Earth. Now, typically energy propagates in all directions from a source. And a ray is just that part of the energy that takes off in a given direction from the source. And we often call that angle that it takes off the takeoff angle. So in this case, it's theta sub 0. For a given ray in a layered Earth where velocity increases downward, ray parameter P is constant along a given ray path. A smaller takeoff angle translates into greater distances of where the ray path emerges at the surface. This also corresponds to a smaller ray parameter, since a smaller angle gives a smaller sine, thus a smaller ray parameter. For a given velocity structure, every ray parameter maps into some distance from the starting point, and that takes a specific amount of time to get there, which of course depends on the velocity structure. So we can create a plot of ray parameter versus distance, or ray parameter versus time. So here's an example. Here distance is given by delta, and the takeoff angle is given by theta sub 0. So the ray parameter is sine of theta sub 0 over the velocity in the top layer. And this particular ray parameter would correspond to 1 point with distance delta. And we can also calculate the travel time. And that travel time is the time it takes to propagate through the Earth and come back to the surface. And that will show up as 1 point on a plot of time versus delta, or x, depending on how we want to define our distance. And dt dx, which is the slope, is equal to the ray parameter. because this is 1 over the distance that it travels at the surface, or sorry, it's the time over the distance it travels at the surface. We can create travel time distance curves for different phases, and these are things that reflect off different layers in the Earth. So here's the travel time versus distance for a P wave, and travel time versus distance for an S wave, for instance. So the ray parameter is constant for a given ray path. The slowness vector can be decomposed into its horizontal and vertical components, where u times sine of the angle of incidence is p, the ray parameter, and u times cosine of theta is equal to eta. All right, so that was a quick overview of rays and ray parameters, and we'll get back to some of these topics later on in these lectures. Now I want to look at the amount of energy that's reflected and transmitted at an interface. So imagine I have an interface, an SH wave. So our displacement in the x direction is going to be 0. Our displacement in the y direction, so that's in and out of the screen here, is going to be u sub y as a function of x, z, and t. And u sub z is also going to be 0 because that's the SV wave. So we're just talking about particle motion in and out of the screen. And let's examine what happens at the interface. So we'll consider 2 boundary conditions that apply at z equals 0. So z equals 0 is the boundary between medium 1 and medium 2. We will assume the wave is continuous, and we'll assume that tractions are the same. So recalling that P equals sine theta over V equals K sub X over omega, and eta equals cosine theta over V equals K sub Z over V, then we can write the harmonic wave propagating in the XZ plane as A times e to the I omega t minus K dot X, where K is the wave number vector. And because there is no propagation in the y direction, right? It's not moving in the y direction, it's just moving in the x and z directions. We just have K sub X times X minus K sub Z times Z. There's no K sub Y times Y. And if we note these relationships here, K equals omega over V, K sub X equals omega over V sub X equals omega P equals omega times S sub X, where S sub X is the horizontal slowness, and K sub Z equals omega over V sub Z equals omega times eta equals omega times S sub Z, where S sub Z is the vertical slowness. Then we can rewrite our SH wave as A times e to the I omega t minus P sub X minus eta times Z. Or since P and eta are the X and Z components of the slowness vector, we can just put these two into S and call X and Z the location vector, which we're going to call X. So since we're considering a SH wave that vibrates only in the Y direction and is propagating in the XZ plane, we know U sub X and U sub Z will be 0. So U sub Y will be the only thing that we have to worry about. So we have a formula for U sub Y. And next, we will define the ratio of the vertical and the horizontal wave numbers to be R sub alpha or beta, depending on whether I'm talking about a P wave or an S wave. Since right now we're talking about an S wave, it'll be R sub beta, and that'll be K sub Z sub beta divided by K sub X. And the reason that we have the subscript on it is because the vertical wave number is going to change with the velocity of the medium. So in the top medium, we have a wave propagating with amplitude B sub 1. And here's the equation that represents its propagation. We're going to have a reflected wave with amplitude B sub 2. And now I'm going to take K sub X and K sub Z and convert that to K sub X and K sub X times R sub beta. And we're going to do beta 1 because we're talking about reflection in the top layer. In the bottom medium, so in medium 2, we have B sub prime, and that's the amplitude of the transmitted wave. And we have R sub beta 2 because that is the ratio between the horizontal and the vertical wave numbers in layer 2. So the first thing we can note is the displacement that has to hold at t equals 0. We can say the incident wave plus the reflected wave, so the top layer, what's happening in the top layer, is equal to what's happening in the bottom layer. And since t and x are 0, if we solve this boundary condition at t equals 0 and x equals 0, then b sub 1 plus b sub 2 equals b sub prime. The second thing we can do is solve for tractions. So traction in the I direction in the top layer is going to equal traction in the I direction in the bottom layer, and these will both be solved at z equals 0, so right at the interface. At that interface, the normal vector is 0, 0, 1, and we know from Cauchy's stress theorem, which we did in the previous lecture, T sub I, so the traction vector is going to be equal to the stress tensor times the normal vector. Since the normal vector is going to just be in the z direction, n sub x and n sub y are going to be 0. And so the traction equations will just be, the traction vector will be sigma sub xz, sigma sub yz, sigma sub zz. Now, because the SH is vibrating in the y direction, the only non-zero stresses will be sigma sub yz, but I want to show you that sigma sub xz and sigma sub zz are also 0. So to get stresses, we will recall that sigma sub ij equals oops. No, it's not letting me go backwards. There we are. Sigma sub ij minus lambda e sub kk delta sub ij equals 2 mu e sub ij. So this is the isotropic relationship between stress and strain. In longhand, so writing this all out and writing in x, y, and z components, I'm just writing this big tensor here. However, since u sub x and u sub z are 0, because the vibration is only happening in the y direction, the only non-zero derivatives are d sub uy dx and d sub uy dz, and stress simplifies to the equation I show here. And the only non-zero traction is T sub y equals sigma sub yz times n sub z, which equals the shear modulus times du sub y dz. Because this green circle gave our traction vector with respect to the z normal, and the only non-zero component is T sub y, which is given here, and that equals the shear modulus times du sub y dz. So our tractions become, in the x direction 0, in the y direction mu times du sub y dz, because du sub x, u of x is 0, so this is 0, and t sub z is also 0. So now we can solve for attractions at the interface by setting these two sigma sub yz stresses to be equal. So sigma sub yz at above the medium D interface is going to be d mu times d mu sub du sub y dz, and du sub y dz equals I k sub x r sub beta 1 times beta 2 minus beta 1 e to the I omega t minus k sub x times x. And this, I'm just taking the equation that we had for u sub y and then taking the derivative with respect to z. In the bottom layer, sigma sub yz equals I sub mu 2 k sub x r sub beta 2 b prime e to the I omega t minus k sub x times x. We're going to set these equal to each other, cancel out common factors to get mu sub 1 k sub x r sub beta 1 times beta 2, or sorry, b2 minus b1 equals mu sub 2 k sub x r sub beta 2 times b prime. And we will recall that b1 plus b2 equals b prime. Now we will define the reflection coefficient as the amplitude of the reflected wave over the amplitude of the incident wave, so b2 over b sub 1. We will define the transmission coefficient t as b sub prime, so the amplitude of the transmitted wave over the amplitude of the incident wave. And here we get then the reflected and transmitted coefficients. We can note that r sub beta sub I equals c sub x cosine j sub I over beta. And then also use the relationship for shear wave velocity, that the shear wave velocity in layer I is equal to the square root of the shear modulus in the layer over the density of the layer. And that gives me the reflection coefficient of R equals the density in layer 1 times the velocity in layer 1 times the angle of incidence that it has in layer 1 minus the density in layer 2, the velocity in layer 2 times the cosine of the angle of incidence in layer 2 over those two terms summed. And the transmission coefficient equals 2 times rho 1 times beta 1 cosine j1 over the rho 1 beta 1 cosine j1 plus rho 2 beta 2 cosine j2. So we have the same denominator in both the reflection and transmission coefficients. One can follow a similar method for P and SV waves. However, when a P wave bends at an interface, like due to Snell's law, continuity of traction and displacement also produces an SV wave. And I will show you the equation that will represent in a minute. But first, I want to note that density is a parameter in the reflection and transmission coefficients. So seismically, you can often get at the density of a layer. And in active source seismology, there's a concept called amplitude variation with offset. And that will tell you the aspects of the density of a layer. So for a incident P wave, the derivation becomes a little more complicated. It's still pretty straightforward. I'm not going to go into it here, but the reflected P wave and the reflected SV wave, the transmitted P wave, and that should say the transmitted SV wave, not T sub P, are going to equal this large matrix times this set of equations here. And this should say, I think, oh, I don't know. I think that should say phi, actually. I'm sorry, I don't recall what phi represents. I think it's the incidence angle in the second layer. So in any case, we have a reflected P wave, a reflected SV wave, a transmitted P wave, and a transmitted SV wave. So that gives the reflection and transmission coefficients for an SH wave and a P wave. And now I want to talk about a couple concepts that apply to ray theory. So Fermat's principle states that the ray paths between 2 points are those for travel time is an extremum, so for which you get a minimum or maximum travel time. So if I have a source and a receiver, the travel time for a direct path will be the minimum time, which is the direct distance between the source and the receiver, assuming a uniform velocity. The travel time for the reflected wave is going to minimize the travel time. There are cases where we get a maximum travel time as well, and we see that with reflected P waves and reflected S waves on the surface of the Earth. So if I can put my travel time into a formula, T sub X, then I can solve for dt dx, and that will give me a possible ray path. And we can actually use it to derive Snell's law. So if I have a source at 0, A and a receiver at B, minus C, and I have this sort of geometry with layer 1 of velocity 1 and layer 2 has velocity 2, then the travel time is just going to be the distance over the velocity of layer 1 plus the distance over the velocity of layer 2. And then if I set that derivative equal to 0, that 0 equals this formula here, x over v1 square root of a squared plus x squared minus b minus x over v2 times the square root of b minus x squared plus c squared. And you can do some trigonometry, and that will simplify to Snell's law. So you will get sine of I sub 1 over v sub 1 equals sine of I sub 2 over v sub 2. So x over the square root of a squared plus x squared is just sine of I. Geometric ray theory fails to predict all observations, such as p-diff, the p-wave phase that diffracts around the core and is observed in the p-wave shadow zone. Huygens principle can explain some of these observations. And what you do is you consider each point on a wavefront as a source for new waves, and these will constructively and destructively interfere. So for instance, as this wave intersects the medium, each point on the medium is going to serve as a new source. This leftmost circle is the earliest source, and then they go upwards in time as you go to the right. And if we calculate the constructive interference of the waves produced by these yellow circle sources, we would get this first sort of green line. So the book, Stein and Weissession, and I can give you guys a PDF of that if you want, that is used to derive Snell's law. All right, we have a few more minutes. So I want to start deriving postcritical waves. And postcritical waves has different names. They're called evanescent waves, inhomogeneous waves, or head waves. A common one is P sub n, which is a P wave that travels at the interface between the crust and the mantle. So when an incident wave comes in at an angle larger than the critical angle, so that's an angle larger than allowed to get a transmitted wave, you actually do get a transmitted wave, and it's trapped just below the interface. And you also get a reflected wave, and the reflection coefficient is 1, but there's a phase shift. So if the critical angle tells you the angle at which the refracted wave will directly go along the interface, we'll call that J sub C, and we'll call J sub I the incident angle. If J sub I is less than the critical angle, then we get a reflected wave and a transmitted wave, and the reflection and transmission coefficients of an SH wave are given by these formulas here, R and T. If we have a critically refracted wave, so J sub I equals J sub C, where C is the critical angle, that means your angle is 90 degrees in the second layer. Then the wave travels on the interface, and we have a perfectly refracted wave. The reflection coefficient equals 1. The transmission coefficient equals 2. And then if we have something that comes in with an incident angle larger than the critical angle, what happens is we get a transmitted wave that exponentially decays below the interface. And the reflected wave is phase shifted. The reflected wave has a phase shift of e to the I times 2 theta, where theta equals this formula here. And the decay of the transmitted wave goes as e to the k sub x times the square root of 1 minus c sub x squared over beta sub 2 squared times z. So we will start this derivation, and then we will finish it up tomorrow, or sorry, tomorrow. So some relationships that will be useful in this derivation: R sub b equals the horizontal wave number vector, or horizontal component of the wave number vector, over the vertical component of the wave number vector. The ray parameter is k sub x over omega. Eta is k sub z over omega. So For C sub x, the apparent horizontal velocity of propagation of a wave, Snell's law gives us 1 over C sub x. That equals the ray parameter, which equals sine sub j1 over beta 1, which equals sine sub j2 over beta 2. This is just Snell's law. We can rewrite Snell's law as sine j sub 1 equals beta 1 over beta 2 times sine of j sub 2. At the critical angle, sine sub j2 equals 1. So sine of the critical angle equals beta 1 over beta 2. And beta 2 equals beta 1 over sine sub j sub c. But that just equals the critical angle, or the horizontal apparent velocity. When the angle of incidence is larger than the critical angle, j sub 1 is greater than j sub c. And then sine sub j sub 1 equals sine of j sub c. Here I just show you that sine is constantly increasing. So if j sub 1 is greater than j sub c, then sine of j sub 1 is greater than j sub c. So that means sine of j sub 1 is greater than sine of j sub c. J sub c equals beta 1 over beta 2. Sine of j sub 1 is greater than beta 1 over beta 2, which means beta 2 is greater than beta 1 over sine sub j1, which means beta 2 is greater than the horizontal apparent velocity. So if j sub 1 is greater than the critical angle, that implies beta 2 is greater than the horizontal apparent velocity. And I will stop there because we are out of time. And I didn't expect to get all the way through this lecture. That's fine, because I will have plenty of time in future days to finish this up and get through the other lectures.
Okay, thank you very much, Derek. So this is the end of the lectures for the day 1, and we will meet for the tutorial in the evening, Indian evening, and that will be US morning. Okay, so thank you so much, Derek. Okay, so let's end of this meeting.
All right, and if anyone has any questions, feel free to email me.
Okay, bye.
All right, see ya.